Today we're gonna have lecture 12. Today is lecture 12, which is about entropy, how to calculate entropy. Entropy is a new property associated with a state, and also we can calculate some, maybe usually the heat from this entropy, and we're gonna take what the entropy is. So today is lecture 12, 24. If you remember, the first sentence I said in this course was thermodynamics is the science of energy and entropy. While we were talking about the energy in terms of heat or work, we did not talk much, or even sometimes at all, for now, about the entropy, what entropy is. So in chapter 7, we're going to talk about entropy. This is entropy. So what entropy is? For every state, we have pressure, we have temperature, we have specific volume, we have internal energy, we have enthalpy, a specific enthalpy, specific internal energy. If it's a mixture, we have quality. Today we're going to talk about S. There is a big S, which is entropy. Small s is specific entropy. Entropy is kilojoule per kilogram, per Kelvin. It is. But here it's kilojoule like kilogram Kelvin. Do you know, where did you see this before? The unit of this? Does anyone know? This is entropy. This is specific entropy. Where did you see this, guys? Can somebody tell me?
Specific heat?
Exactly. See, similar to specific heat in units. It's a heat per unit mass, per unit temperature, but it's not exactly a specific heat. It's a similar in the units. It's even similar in the equations, but it's not similar in terms of definition. Before we go to that, let's start with 7.1. 7.1, we said in the last lecture, for example, if we have heat engine, heat, we have Q high, we have Q low, and of course we have W net. This is coming from T high, this is coming from T low. So heat coming from upper reservoir, constant temperature, dump some heat, get some work, dump some heat in the lower temperature reservoir. Of course, Q high equal W net plus Q low, and we have thermal efficiency. And we have, finally, we get two equations, Q high over Q low equal T high over T low, or vice versa. This is only equal if the process is reversible. If Q high over Q low is reversible, this is the equation. And if it's not, this is different. It's actually less than. So if we did this way, this is not always correct. It's always for Carnot. Yes, Carnot correct. Ideal correct. Reversible process correct. The very, very optimistic design we can have. The best design we have. Yes, that's correct. Let's rearrange this and write it something differently. Let's write it Q high over T high equal Q low over T low. Do you think I did something wrong, guys? I just use this, push it up and put it down, like cross. Let's also take this to the other side. This equation is so important. Mathematically, we can say this equation, guys, where is it? Where is my red marker? Yeah, here. Yeah, we can use this equation as delta Q over T. As we talked before, we have two things. We have delta and we have D. This is called exact. This is inexact. If it's a property, it's they, like dP, dt, dV, ds, for example. But if it's not associated with a state, it's delta, like delta work, delta Q per unit mass. So delta Q, uppercase or lowercase, absolute Q or per unit mass, over T is equal to this. This is the integration of that. This is the definition mathematically. Okay, so everyone agree with me? This equals 0 if it's reversible. If this is reversible, of course it's 0. This mathematically means that. Mathematically mean that. Okay, so this guy, guys, always in reality, lower than 0. So delta Q over T, which is this guy, lower than 0. And this is called or equal. Equal means reversible. This is the reality. If it's irreversible, it's lower. Q high over T high minus T Q low over T low, lower than 0. Lower than 0. I will give you an example if you want. Do you want guys example about this? How can make less than 0? It's so simple. Look at this. Look at this engine. Look at this engine, guys. Let me take 2 colors. Okay. Let's talk about 2 engines. One engine here. One engine there. That's another color. Okay. Let's assume now, guys, 2 engines. One, both of them dump the same Q. This Q, the same as this Q. The same heat coming from the same source. And actually going to the same reservoir, T low. But this one was Carnot, ideal. This one was not real. This Carnot, ideal, but this is not. What happened, guys? In Carnot, I get less work. In Carnot, get more work. This W net is much bigger. This W net is much bigger. It's much bigger here. It means Q low reversible is smaller than Q low irreversible. So because I got more work, of course, this equal this plus this. Of course, I get more work if it's reversible. It means Q lower reversible, it's lower than Q lower irreversible. Q high is the same. So Q high is the same. So if it's reversible, Q high over T high minus Q low over T low, it's equal to 0. Equal to 0. But Q low irreversible greater. So this term, in terms of irreversibility, is bigger. Something minus something, this term became bigger. Something minus something, and this something here irreversibly is bigger. Does anyone agree with me or not agree with me? Q low reversible lower than Q low irreversible. If anyone has objection, let me know now, please. Q low reversible lower than Q low irreversible. Do you agree with me or not, guys, with this statement? Because this is ideal, I got more work. W net here, reversible, lower than this, greater than this. So this guy is the same. I get the same source, the same heat. Of course, this is lower, reversibly. I dump lower losses here in reversible, but I dump here a lot of losses. Irreversible is a lot. I lost a lot. It means this guy is bigger in a case of a irreversible process, a reversible process. So this equation is negative. Locally, delta Q over T, locally. And we call it Clausius inequality. This guy is called Clausius inequality. This is called Clausius inequality, page 2 in your lecture 12. That's cool. That's very cool. Let's go to define property again. So this is always correct. Delta Q over T locally is negative, locally, not globally. So again, guys, So what is property again, guys? What is property? Can somebody define for me a property? First lecture. What the property is? Huh? What's the property, guys? Huh?
An intrinsic value with a
It's exactly. It's a characteristic. It's something define a system. Pressure, temperature, volume. It's a characteristics. So what's if you plot, for example, let's say TV diagram, for example, and you started here. This is certain like volume, temperature, point. It's point x, y, x and y. Let's say V and T. And you did some process 1, process 2, process 3. If you go back to this point, we call it a cycle. This point, if it's a cycle, of course, this delta V would be dV would be 0. Delta U would be du would be 0. It means U1 minus U final equals 0. Of course, because this is the same point according to cycle. So that's how we define a property. If we start at a point, any point, and we go do whatever we did, and we return back to this point, if it is the change is 0, it's a property. Let's talk about work. If you started here and did some work, some more, some more, some work, it is not 0 because it's this area. If it's PV diagram, this area is the work. So when you go back here, there is a work. So it's not 0. It is not. That's why delta work is not a property. The same for heat is not a property. If you go from here and you turn it back, actually the best thing to plot heat is TS. I will tell you why now. So if you go this, and you turn back here, delta Q not equal to 0, but delta U equal to 0. That's why we call it du, dV, dt, ds, because they are properties. Delta Q, guys, not equal to 0 at this point. If you start here and you go, and turn it back, it is not 0. You know what is this, guys? Do you know what is this? Delta Q here? It's area here. PV diagram give you work. TS diagram give you Q. That's how we define Q. How we define Q. So delta S or ds is delta Q over T. So S or delta S equal a chain or integration of dq over T. Let's talk it about generally like this. So S2, again, if you remember, guys, when we talk about work, we define work as PDV. PDV. However, delta work itself does not go to 0, but pressure alone go to 0. It means change. dP equal to 0 at this point. dV itself go to 0. But PDV is not 0. So at this point, if you start here, go and turn back, delta pressure is 0, of course, because it's a property. Change in pressure is 0. P2 minus P1, P2, P final minus P1 is 0. The same here. dV is 0. I started here, ended back here. It's 0, of course. But PDV is not 0. It's a work. So if you start the work itself, work only, work on heat. If you started here and you go back, heat is not 0. But if you go like this, this is 0. This is 0. If it is reversible, if you go for the whole system from the beginning to the end, delta Q over T, this is equal to 0 if it's reversible. So we give it a property name. We call it entropy. Joule per Kelvin. Joule per kilogram Kelvin. So joule per Kelvin or joule per kilogram Kelvin. So delta Q does not reach 0. That's 100% correct. But dQ over T should go to 0 if it's reversible. dQ over T should go to 0 if it's reversible. And we call it entropy. So always ds equal this. The most famous delta S, guys, it's what? If this temperature is constant, for example, a special case, a very important special case, delta S equal Q over T. If temperature is constant, if T equal constant, which is, for example, T0. So always delta S Q over T. First of all, do you understand this, guys, this part or not? Let me know now. I want to make sure that everyone understand this part. If anyone has any problem with this, guys, let me know now.
So for the cycle, the delta Q doesn't equal 0,
Of
but delta
course,
Q over T does equal 0?
if it's reversible.
Okay.
If it is reversible, that's what we showed here. We said delta Q over T equals 0. When? If it's reversible. If it's not, negative. We said we know 100% Q high over Q low equal T high over T low. Q high over Q low over T high equal Q low over T low. This, guys, means the difference is 0. Of course, it means, so if you have something like this, delta or D, what's the difference between those mathematically, guys? Delta and D. Let me explain it for you. Maybe you know it, but you forgot it. I'm gonna write this back, but let me now write for you mathematics, some of basic mathematics. What's the difference between this and this? We said it before. If you have integration of delta V between 1 and 2, it's V2 minus V1, because integration of 1 is V. So it's V2 minus V1. But integration, for example, delta W does not equal to W2 because W is not a property. Of course, this is correct or not, guys? We did talk about this before. This is correct or not? The difference between exact differentiation and inexact. Hey, guys, this is correct or not? Can anyone say no? Yes?
It is.
It is always correct. But why? You know why? Because this is called path independent. This is path dependent. This is the only difference. In mathematics, if you have local D, but you have this delta, this is difference. This is path independent. I don't care where I go, from where to where, how I go. But the final minus end is my change. Of course, integration of 1 here means V, but this is not. This is path dependent, path independent. This is exact, this is inexact. So if we have delta Q, so if you have delta Q, you cannot say it's a Q2 minus Q1. That's wrong. That's totally wrong. But if you have delta Q over T, and I told you it's a property, let's now assume it's a property. It's Q over T. Let's say you make big Q. Q over T minus Q over T. We start from, let's say, low to high or high to low. It's a high over high, low over low. If I told you a cycle started from a point, go to the same point. It started from certain pressure, temperature, and volume, and you go back to the same thing. It's reversible. Of course, this is 0. If you start from certain volume and go back to the same volume, of course, V2 minus V1 is 0. If you start from the same state and go back to the same state, this difference what is 0. Yeah, it's correct. If it's reversible, we said Q high over T high over Q low equal T high over T low. So this minus this equals 0 if it's reversible. So this now, it's a property. And we call it S. We call it S. So everyone, please open table 4, for example. Open, please, table A4. Everyone. Everyone, please open table A4. Okay, guys. For steam table, if you look at the steam table, A4, temperature is input. So you have the first left column is T in Celsius. Next one is pressure, P, saturated pressure and temperature. Between G and from F to G, from liquid to vapor, from X equals 0 to X equals 1. You find the next two columns is VF and VG. VF and VG. VF for X equals 0 and VG is for X equals 1. For example, if you go at temperature 100 Celsius, go down at temperature 100 Celsius, you will find the pressure equal to 101. It's almost 1 atmosphere, 101 kilopascal. Correct, guys? Make sure that you are following me. At temperature 100 Celsius, the pressure is 101. The volume is 0.001. That's a number we know. 0.001 something, 11 something. It's called 1 liter, which is 0.001 meter cube per kilogram. This is exactly a liter of water. Something like this. Water bottle, it has 1 liter. It's exactly 0.001 something meter cube per kilogram. The next one, the next column, which is VG, it's 1.67 meter cube over kilogram, which is what? This water liter. If you heat it up until it became totally vapor, the volume became almost 1 meter cube, almost 2 meter cubes, 1.67 meter cube per kilogram. So this water in liquid phase, very small, 0.001 meter cube per kilogram. If you heat it up, became completely vapor at the same pressure, the same temperature, 100, it will be completely vapor at a volume of 1.67. Correct, guys? Can you follow me, guys?
Yes.
The next three column is called internal energy, UF, UFG, and UG. UF, internal energy at the liquid phase, UG at vapor phase. The next three and UFG is the difference. If your next three is enthalpy, enthalpy is U plus PV. U plus PV. Internal energy plus flow work. The last three, guys, is entropy. Look at the last three, guys. Entropy. SF, SFG, SG. So whatever you did with for U and H, V, you can repeat it for S. For example, for first of all, S, guys, or delta S equal to this. Always. This is the definition of delta S. We don't care about U, internal energy. We don't care about H. We care about delta H. We care about delta U. We care about delta S. So we always care about the change in S, not S. Delta S. Yes, we have local properties, but we care about how this property changes. That's how the heat look like and stuff like that. So let's talk about, for example, mixture. For an instance, mixture, guys. If you have a mixture and you have the TS diagram, for example, the P or TS TV diagram. In TV diagram, there is a new property. We call it S. So in TV diagram, guys, the pressure constant like this. The entropy constant like that. S equal constant. In the exam, I'll ask you, in the V diagram, plot S constant. This is the S. S related to Q, which is somehow related to temperature. So S increases, or actually constant, T kind of increases. This is the constant S line, different from PV. In the PV, S look like the volume decreasing, of course. That's why it goes down. So here, this is the constant volume line. Let's say this is V equal constant. This is constant temperature line. This is constant like pressure line. For example, the green line is constant pressure line. The black one, let's say this is the black one, is constant temperature line. The vertical one, constant specific volume. So there is something called entropy, like this. S. If you are here, S equal SF. If you are here, S equal SG. If you are here, S equal SF plus, huh? Can somebody tell me? Plus what?
SG.
XSG. FG. X, quality first.
My bad.
The same equation we use for V, specific volume, we use it for internal energy, the same valid here, everything applied. But remember, S is dQ over T. Q itself is not a property, but Q over T is a property. We call it S. We call it S entropy. It's a measurement of randomness of a system. Measurement of randomness of a system. Hey guys, can you follow me? Any problem here, guys?
Mm-hmm.
So the good news is,
Yeah.
could you please make it some mute? So make sure, guys, you are, if you used to laugh, make it mute, okay? So delta Q over T is S. If T equal constant, which is a very important special case, S equal Q over T. Let's say T0, for example. This is very important. A special case. If T is constant, generally, is delta Q over T. Guys, can someone tell me what system or when we can see T constant? Something, you give it heat or take from it heat and temperature remain constant. What is this? Can somebody tell me what is this? What is the body that has infinite thermal capacity? If you dump it heat or take heat, temperature remain constant. What is this, guys?
A thermal reservoir?
Exactly. Temperature remain constant for reservoir. So if you have system and you have boundary, of course, outside we call it surrounding. We have here, guys, 3 delta S's. We have 3 delta S's. Delta S surrounding. Delta S surround. Delta S system. We have delta S generated. Delta S generation, which is this plus this, is called delta S generated. So delta S generated equal delta S system plus delta S surrounding. Usually surrounding, if it is a reservoir, we can use this. If it is reservoir, thermal reservoir, reservoir. If it is a reservoir, thermal reservoir. So guys, if this system is 2 components, like let's say this is one here and one here, so delta S plus delta S equal delta S system. 3 components, 4 components. Delta S system is this plus this plus this plus this. Surrounding is one term. Systems can be subsystems. All of them is called delta S system. Everything is called generation. Systems, let's say system 1, system 2, system 3, subsystems, plus surrounding is called generation. This guy must be greater than or equal 0. So maybe system is negative, maybe surrounding is negative, but of course the other is positive. But the total should be greater than or equal 0. If it's equal to 0, that's adiabatic and reversible. That's called isentropic. So delta S only equal to 0 if adiabatic and reverse. Of course, generated entropy, this plus this. System plus surrounding. We have two things, system and the surrounding, everything outside. Inside, we have some change in entropy. Outside, some change in entropy. The total is called generated. Okay, guys? Always greater than or equal 0. Let's take an example. Let's stop here and this one and take an example and come back. Please read problem in the exam, problem 7.1. Problem 7.1 in the textbook. Example 7.1. Example 7.1. Can everyone read example 7.1? It's so simple. It says you have a tank or you have a system. Example, this is example, no problem. I'm making a very simple example, 7.1 in chapter 7. So we have a system. It has temperature 300 Kelvin. It has, I add heat by 7.5 kilojoule. He wants entropy. So this solution is so simple. I had some temperature, I add some heat. So delta S just equal to Q, delta Q over T, which is temperature is constant, so just Q over T. So it means 7.5 kilojoule over 300 Kelvin. It is 2.5 kilojoule per Kelvin. This is delta S here, delta S system. By the way, delta S system can be negative. Delta S surrounding can be negative, but delta S generation must be positive. So this can be positive or negative, but the generation, the total is, okay, guys? Guys, is it simple? Just Q over T because temperature is constant.
Yeah.
Okay, oh, read for me, please, problem 721. Problem 721. 7 problem. This is problem. Problem in the book 721. I give you a minute to read it. Please read 721. So problem 721, guys, he give you two bodies. One is at 1200 Kelvin, one is 600 Kelvin, and there was 100 kilojoule transfer from the hot 1200 Kelvin to the cold system, which is a cooler system, which is 600 Kelvin. He said calculate the delta S source, delta S sink, and does the entropy principle satisfy? Does the delta S generation is greater than 0 or equal to 0 at least? Of course, delta S generation is not negative. So he said the heat goes from the hot to the cold. So we have here, let's draw it in the simplest. I'll keep now delta S generation because we want it. Let's redraw this again. 721, guys. Problem 721. If you read it with me, 721. He said 1200 Kelvin. This is a system or reservoir or body. Transfer 100 kilojoule to 600 Kelvin. Like, for example, something like very hot ball of steel, put it in water at 600 Kelvin. So the heat transfer from this to this. from this kind of perspective, it's look like correct. Goes from high temperature to low temperature. That's what we said in the first law of thermodynamics, correct. Even if it's like this, in the first law of thermodynamics, it's correct. But second law said, no, that's not correct. Let's see that now. So delta S generation should be greater than or equal to 0. 0 if it's reversible, greater, which is reality, and it's impossible to be negative. It's impossible. Let's see that here. So delta S source, this guy, delta S sink equal to what? Can somebody tell me delta S source equal to what? Delta S source, guys, or delta S sink? What is this? Because temperature is constant. What can I say, guys?
It's Q over T.
Exactly. Go over T source. Q 100 kilojoule over T, which is 1200 Kelvin. Look, guys, I'll give you some important thing. You remember when we said when Q like this, that's actually may confuse you. Let me okay. This is Q negative or positive, guys, in this form. Usually we talk about heat addition. This heat kind of leaving the system. It's leaving the system. It's positive or negative?
Negative.
Perfect. This is negative. This is negative. But here it's the same Q but positive. Why positive? Because it's added to the system. Heat addition positive. So here it's 100 over T sink is 600. So you got here number and here number. Here number would be negative small number because divide by 1200. Here is big number 600. Here it was let me write it from here, negative 0.0833 kilojoule per Kelvin. Here it's 1 over 6.1667 kilojoule per Kelvin. So delta S generation, all the delta S's, we have only this and this. So delta S source plus delta S sink. All the delta S's look like system and reservoir and so on. So it's negative 0.0833 plus 0.1667, which is positive 0.0833, I think, kilojoule per Kelvin. Does this make sense, guys? Does this make sense?
Yeah.
Of course, makes sense. Why? Because heat goes from hotter body to cooler body, from high temperature to low temperature. Do you remember the cup of coffee example? I told you if you hold a cup of coffee and the cup of coffee get colder and colder and you get warmer, and or vice versa, the heat of coffee get warmer and warmer and you get colder and colder. So the heat go from your body to the cup. That's correct in terms on front of first law of thermodynamics. So this gets warmer and my body get colder. So heat goes from cooler to hot. That's correct in front of first law of thermodynamics. Sangan said, no, that's not correct. Let's take this now. In problem 722, he said, okay, reverse the heat. Let's the heat going this way. The red one going upward from the cooler to the hotter. Now, delta S source, or this one, for example, which is not source now, the heat going inside, it's positive or negative? It's opposite. It will be positive because heat addition, heat addition, heat addition. So 100 kilojoule over this, it's positive because it's going to the 1200. Delta S sink, which is now 600. Now the source became sink, sink became source, but delta S of 600. It's going out. It means negative. So it's negative, negative. So this plus this will be finally opposite, negative. Negative sign, exactly everything, but delta S generation will be negative 0.0833 kilojoule per Kelvin. Does make sense, guys?
So the value of the delta S will depend on which direction of the process the
No,
problem gives us?
no. The Q depends on the sign. The Q,
Oh yeah, well yeah, the Q which gives
yes, be
either positive
specific.
or
I
negative.
always, look, when I say Q, I don't say, for example, you have never ever hear me, for example, say a specific heat. You will always hear me what? Saying heat per unit mass. Correct?
Yeah.
Why? Because there is no specific heat. Heat is specific only a property, specific enthalpy, specific entropy, specific internal energy, specific volume. But you will never ever hear me say specific. So we need to be dedicated to definition. Heat is positive. It's addition. Oops. Negative, it's rejection. Make sense? Okay.
Yeah.
So that's also reflected in the delta S, but not delta S itself. It's Q result final in delta S, because we were lucky in this is temperature were constants. Many of the cases temperature is not constant, like what we're gonna see. That's why we have steam table, we have even ideal gas law, and we have special cases. So delta S, if temperature is constant, yes, you are right. Heat addition, positive, delta S positive. Heat rejection, delta Q is negative, delta is negative, okay? But generation must be positive, greater than or equal to 0. This is impossible. Impossible heat goes from cooler body to hotter body. The red one, it's impossible to happen. Okay, guys? This violates the entropy. Okay, guys? So
Yeah.
please open page 5. Please, everyone, open lecture 12, page 5. Lecture 12, page 5. I'm gonna move this. Can you please read it with me, guys? We have 3 principles of entropy. They are very important. Definitions and principles, like Carnot principles. I may not ask you directly, but implicitly in a problem. So the first one, process go in certain direction. That's the first thing we talk about in the second of thermodynamics. Only processes only can go in certain direction. Total entropy should increase always.
Professor, can you let the camera focus for a second? It's kind of blurry.
Okay, sorry. So if you go, please, page. Actually, we can take break now, and we can come back at 11. Okay, guys? Okay, guys?
Yeah. Yeah.
Okay. Now it's better, but let's come back at 11, okay? We have a page. Now let's continue. As I said, please go to page number 5, lecture 12. You will see that the process only goes in certain direction, which is a generation of the entropy should be greater than or equal 0. Equal 0, it's always increases. Equal 0, it's isentropic. There is no generation of the entropy. So entropy is non-conserved. Entropy is not, oh, that's strange. Is not conserved. So always entropy increases, is not gonna decrease. Look, guys, we are lying here. However, entropy increases, yes, always, but because of we have waste energy. If we be able to reuse this waste energy, which is we cannot, the entropy will decrease. So whenever you heat, for example, let's say you make a coffee, you heat something in the oven, use microwave. Of course, all of you use microwave. some of this heat escaped to the ambient. Of course, you are heating up in microwave. Let's say you paid, for example, 200 watt. Some of this escape. When you heat up, you find that finally you used 150. So where is the 50? You dump it in the ambient. It means the S surrounding increases. You got more heat dumped in the ambient. 50 watt, the remainder of this, let's say 200 watt, dumped in the ambient. That's why it's always increased, it's not conserved. But if we be able to dig this back, what we wasted or dumped it in the ambient, of course, which is we're supposed to do that. If we be able, which we cannot, if we be able to return them back, delta S will go back to as it was. Okay, guys, does it make sense for you? When you heat something, it's impossible to return it back. Whenever you have heat, that's why we said adiabatic and reversible. If you have no heat at all and a very pure system without friction, without restrained gas or any problem with the reversibility, you have isentropic. But once you have heat, you have, of course, delta S. Of course, no way. Okay? Okay, guys? Okay, guys?
Yeah.
So delta S is a measurement. Yeah, thank you for making it quite now. Of irreversibility. So sometimes irreversibility, this is RR, double R. So we use delta S to measure irreversibility. We wish we have 0 delta S. So if you have two designs, design 1 and design 2. The design 1 gives you delta S equal, for example, 0.2 kilojoule per kilogram. Design 3, okay, let's say this, 0.5 kilojoule per kilogram. Which one is better, guys?
The one with 0.2.
That's not correct. Now, guys, which one is better? I'm so happy you said that, guys. Both of you, be quiet. If I give you the mass here equal 1, or the same mass here and mass here, yes, you are right. This is better. But if the mass here, for example, much lower than here, so this design is better. So if you have design 1 and 2, so because I did not say specific, if it's specific, you are completely right. It's specific, yes, yeah, of course, the first one is better. So we need always to care about design size, and so the first one now is better, of course, because it has lower entropy generation, because it's per unit mass. Because if they do designs and do different masses, maybe this is better, because the mass is much larger than here. So maybe this is better if we divide by larger mass and it drop down. You got it, guys? So do not just blindly look at one number. Look at a number and its unit. The units give the real value of a value. So it's kilogram Kelvin, or Kelvin kilogram. It's kilogram Kelvin. Okay, guys? So now the first one is better, of course, because the mass or the, oops. So guys, yeah, in the midterm, I was so tired. I get tired from you guys. You are doing everything to make me get mad. I don't know why. So make sure, guys, when you solve the midterm or anything, make it easy for me in quality of scanning, in the writing. So some of you, I don't know why. You like hiding the answer. I don't know why. I'm not your enemy, guys. Like write the answer. Let it clear, like clear and clean. So do not hide your answer, please. Okay, guys? So most of you, they have correct answer, but they hide the answer. They scared. I don't know why. So please always make sure that you have your answer clean and clear, very clear. This is very, because I gave grade based on the steps more than a lot of you have some mistakes, but they get a very good grade. Let's say 18 out of 20. And the whole problem is wrong. Some of you have most of the problem is wrong. You got number correct, you got some point off, the rest is good. I took his number and continue. He got 18 out of 20. Many of you, by the way, many of you. In some problems, get a very good grade because I always follow. That make me tired, but it's okay. I'm always looking for your benefits as well. Okay, guys? So we talk about everything here. Yeah, let's take some examples. We said that we have, this is 7.3. The steam table or the steam charts, we have two things, steam and we have ideal gas. We're gonna talk about ideal gas next time, but for now, steam table. Steam table, guys, now updated. So if you have, for example, the TV, the PV, so we have three principles. Delta S always greater, it's not conservative, it's a measure of irreversibility. These are three basic principles of entropy. So if you have, for example, PV, and now we have TS. You know, this is very good for work. This is very good for heat. Because the area under the curve is work here, area under the curve is heat there. Very good. This is very good for work. Very good for heat. Because Q is T delta S. Or delta S is delta Q over T. Both are the same. Both are correct. The heat you paid is area under the curve T delta S diagram. TS diagram. Here, work is exactly PDV. Under the curve. This one does not have any of these, but it's also good. So the first one we started with, if you remember, for example, we said if you have constant pressure line like this is constant pressure line, P equal, for example, 1 atmosphere. This is constant temperature line. We have now constant entropy line. Let's say something like this. This is S, it goes vertically, very vertical like this. S equal constant now. And we have charts. Table A4, A5, A6. Let's take some examples. I give you T equal 300 and P equal 150 kilopascal. Find S. Please, everyone, let me know what S is. Let's say you have a state. I think this state would be here. A certain pressure, temperature here. You have a certain pressure, a state here. I want to get the entropy here. To make it easy, make it now 200 if you want. 200 easier. Hey guys, what's the entropy here? So if you go first, let me share with you. Guys, do you have any questions? I said page 5, 12.5. Principles are page 12.5. Lecture 12, page number 5. Let me share with you now, for example, the steam table. Let's see here. Okay, first of all, if you go, you're gonna start with table A4 because temperature is given. Temperature was 300 Kelvin. 300 Kelvin. Let's see, this is table A4 for water, but table A11, 12, 13 for refrigerant 134A. So it's water here, temperature 300, it's here. So the pressure is 200 kilopascal, but it's here, it's 8,000. Oh, that's very huge. It means I am superheated. My pressure is much, much lower than saturation pressure. It means I'm superheated. So go to where? Table A6. Go to table A6. A6 here. This is A6. My pressure is 200, which is 0.2. So 0.2 megapascal is here. So go to pressure, temperature of 300, this one. So the first value, guys, can you see me, guys? This is what? What is this value? Hello? Guys?
Specific volume.
Perfect. Meter cube per kilogram. How about this one? Specific internal energy, a specific enthalpy, a specific entropy. So the answer to this question is 0.2. If it's 0.15, you need to get this value plus this value at 0.1 and 0.2, this one plus this one over 2, interpolation or average here. Okay, guys? Okay?
Oh, yeah.
Okay, so this means the solution for this problem, just 7.8 something. So go to table, start with table A4, you will find this is superheated because your pressure much lower than saturation pressure. Go to table A6, you'll find this value. If it's between two values, so you need, if it's 150, so you need to get S at 0.1 plus S at 0.2 divided by 2 for interpolation. Okay, guys? Like 8.2 plus 7.9, average them to get the S at 150 kilopascal. Okay, let's take another one. He said you have, let's say, temperature 400 Celsius and entropy was 4.32. Sometimes in some problems you have entropy. Find, for example, the volume, a specific volume. So let's start with table A4. This is still water. Let's go against table A4 because temperature is input. If it's pressure, go to table A5. Start with the table A4. So what this is, guys, if you go to table A4 again, let's share with you. If you go back to table A4 with temperature as input, 400 Celsius, it's a very, very large temperature. It's even, oh, it's not in the table. Let's make it 200. 200 Celsius. 200 Celsius, it's the table, the critical temperature is here. So everything above that, it's superheated, of course. 200 is here. Can you see this, guys? Can you see this? So I said temperature is this, and let's say this is 3.3. 3.32. Let's say this is example. This is your example. Find for me the volume. Or energy, U, or U, or H, or anything. I want U, for example, U. So the temperature was 200 Celsius, and the S is 3.32. So here, guys, the temperature is 200, and this 3.32, for example. Find the U, internal energy. So temperature is 200. We need to go to this one, and at the last row, which is temperature 200, we have here. Okay. So you are between 2.23 and 6.43. This is UF. Because you are in between. What's your status, guys? What is this description for this state? What is description for this state, guys?
A mixture.
Exactly. Because you are in between this point and this point, you are a mixture. It's here. So this is 2 point something, this is 6 point something, and you are 3.3. So you are in between. You are in between. So this is greater than SF, but less than SG. It means you are saturated mixture. It means you can get X. So X equal S minus SF over SFG. Because if you want U, V, H, anything at this state, you need to get X, quality. You need to have the quality. The quality is the property minus property at liquid over the difference. So go back and get SF and SFG. They are given, explicitly given. So you get SF, which is this value at this temperature, and SFG, the difference between the gas and vapor. Of course, gas is larger for everything, for volume, for internal energy, for a specific everything, specific volume, internal energy, enthalpy, or entropy, always increases with volume. So you have this, the difference between them, which is this guy minus this guy. Okay, guys? Okay, guys?
Yep.
Yeah.
So, thank you. Yes and no, man. Thank you. You are good. So you have go back here, so you can get X, 0.1, 0.2, 0.3. So I don't know why all of you, almost all of you, do not remember this. We have here X equals 0, saturated liquid, X equal 1, saturated vapor, no X here, no X there. So if you have a table, say there is no X. That's it. You got the total mark. Here in subcode or here, there is no X. There is no X. Some of you say X equal, for example, 12. I don't know how come. So X only in saturated mixture. You are genius, guys. You are making stuff great. Yeah, it's a jokes, but it's great, you know. So X only valid between what?
What if you put X is less than 0 for
There is
that
nothing.
question on the midterm?
There is no X lower than 0. It's impossible. How?
So
X
what was the correct answer? Just nothing? Like
Yeah.
just not to answer the
Nothing.
question?
It's definition of X only in mixture. It's mass of gas over total mass. It means there is, if you have totally liquid defined, there is no actual definition, only valid in saturated mixture.
I understand. I see.
So here there is no X. Here, if you just write the dash like this, 0 is sometimes wrong, but here 1 is also because you can say, that's mass gas over total mass, which is gas, so it's 1. I don't like this, but you can say that. But 1, it means you are in saturated line. I don't want to make this confusion. Always 1 only here. If I said 1 X equal 1 means I am exactly saturated vapor. I'm exactly saturated. There is no X here at all. There is no X here at all. X only in between. And some of you are very talented. You make up a lot of good things, jokes, and anyway, yeah, I can make a day for you guys if you want to see this kind of show of these beautiful results. But many of you are very smart, are very good. They are giving an answer in a very short number of lines. Like for example, the last problem, some of you get it in 2 lines. Some of you get it in 1 line. The last problem, 1 line, seriously. Problem number 4, which is look like the biggest problem, it's 5 requirements. Every one of them is less than a line. Every one. Equation, solution, equation, solution, equation, solution, less than a line. So it's the equation. Some of you, when I give you the grades today, inshallah, today I will give you the answers, the grades. So you will see what's going on. However, I'm not gonna post your solution. If you want to, you need to come to pick up your midterm. So I will not able to scan them. So
Professor, if we're not in the area but we want our exam, can we specifically ask for our
sure,
scan?
sure. I'm gonna
Okay.
upload for you
Thank you.
model answer and the grade distribution. So you, of course, you know what happened.
You can grade yourself. Yeah, I get this, I did this. If you have complaint, talk to me, no problem. I can cover for you your exam, but I'm sure I give you more than what you deserve. So if you come and ask me, I'll give you less because I will give you now the actual grade. Okay? So do not ask. Usually I give more than what you deserve, guys. Okay, guys? Let's move on. No worries. No, I give you what you deserve, but if you are good, I give you more. I need to be good. At least show me you are good.
Appreciated.
No, I gave you if you deserve. If you did nothing, you get 0, of course. If you wrote wrong equation,
Only if you deserve it.
Nice.
exactly. For example, if you wrote an equation which is correct and you don't write anything else, I give you like 70% of the grade. 70%. But if you write for me 4 or 5 equations, it means you don't know anything. You got 0. But if you write the correct equation but you don't know how to use it, that's a different story. Okay, guys?
All right then.
So you need to know what you're writing. If you write everything, you get 0. Don't worry. You are wasting your time and mine. So you get 0. So write what you think it's correct. That's it. Do not go beyond that. And if everything was from. So let's solve some problems. Please read with me 730. Read problem 730 in the textbook. So you need to always open the chapter and open the lecture notes so you can follow with me. So read problem 730, please. So this problem was a rigid tank has some water and some vapor. He said quality 0.25. So you have 3 kilograms of water in a rigid tank with quality 0.25. Quality, guys, is mass ratio. How much vapor to the total mass? Only if you have a mixture between vapor and liquid. Okay, guys? Rigid tank with this initial quality. So he gave some heat. He gave some heat to the system. So I have system, I have surrounding. Surrounding give me some heat. So this system, the energy will increase. The entropy will increase. Surrounding will decrease. But the total generation of the entropy will increase. So this heat energy system, I want to get the delta S12. I want to get delta S12 between state 1 and state 2. State 1, I have 2 independent intensive properties. State 2, I have 2. One is given. He said it went completely from here to saturated vapor, x equal 1. That's why I like to say x equal 1 only at this line, saturated vapor line. But where is the other one? Can someone tell me what is the other one? What is the other property here, guys?
A mixture?
What mixture means? So
It's
what I know,
in the like never mind.
so this is rigid tank. So V2 equal V1. And also I'm still in saturated line. So P1 equal P2. Either correct, both this or this. So from here you can get V1, get S1. V1 is equal V2. Okay? Okay? Actually, this is wrong. So V1 equal V2. Do you know why, guys? Let's slide this. This is
A rigid tank.
exactly. You need to move vertically. So I was here. I need to move vertically. Let's say this way. So this is vertically. Let me plot it bigger. So this is the solution, guys. I was here. I went to constant volume. V1 equal V2. I'm sorry, I wasn't horizontally. This is here. So this is 2 and this is 1. Sorry for confusion. So V1 equal V2. From here, guys, from this and this. Of course, from this guy and this guy, you can get V1, S1, so on. Let's get, for example, V1. What is V1, guys? Can you tell me? Solution at 1. You have P1 equal 200 kilopascal. What is V1, guys? V1 is Vf plus X Vfg, correct? You can get V1, meter cube per kilogram. Vf plus X Vfg, it's exactly 0.22222, 0.2222. You can get, for example, S1. That's what I want. I want S2 minus S1. I can get S1, which is the same way. It's SF plus X SFG. SFG. Oops. Everything is small s to be specific. It's a property. S1 was 2.294 kilojoule per kilogram Kelvin. It's specific. Okay, guys? 2.922. This is 9, 2.9. Okay, guys? So why did I get this? Why I get this, guys? Because this is required. One of them requirements. Why I get this? To get step 2. So add 2 now. Add 2. We have X equal 1. But I don't know where. Where is it? But I know what the specific one is because it's the rigid tank. The volume and the mass do not change. V1 equal V2. So get V1, get V2. So this V2, guys, equal V1, which is 0.2222 meter cube per kilogram. So which table, guys? Can someone tell me which table now? So the black things are given. The red are what I understand. So he gave me this, he gave me that, he gave me this, he gave me that. I get that from rigid tank. So can you tell me, one guys, from this problem, from where we're gonna start? Which table?
A5.
A4 or 5, it doesn't matter. Go to the VG because X equal 1. Search for VG, table A4 or A5. The best, both of them are correct. Look for the best value close to this. You will see a corresponding temperature and pressure. Like let's say this is TV diagram. So this is point, table A4 or 5. Look for the VG only because X equal 1. VG only, the second 1, 2, 3, 4, the fourth column in A4 or A5. Make sense, guys? So let me open it with you if you want. So what these questions are? So I use subscription, like put number down the S to distinguish between different tables. If you do not follow what I said, I just want to show different tables. So here, this one, the VG, which is the first column here, look for 0.222 somewhere here between this guy and this guy. Actually, table A4 does not have a, it's between, closer to this guy. So let's go to table A5 also. Maybe it has better answer. Any 0.222. Yeah, here is better. Here is better, guys. Between this guy and this guy, it's closer to this guy. So it's very close to 850 kilopascal, 172. So look for the VG. It means VG, UG, HG, SG. These are the best values. So interpolate between this guy and this guy to find the best entropy, which is kind of between those two, but closer to. So look at this one. So you can get S2. You got it, guys? Can you follow me, guys, in the tables? So table 5, table A5, much better than A4 because it has more details in the VF or VG. So here between this and this, it's 0.22. Actually, between this and this better because it's 0.222. It's lower, so go down. Between this and this better. Between 172, 175 temperature. These two. I just want between these two interpolate to get between this VSG and SG at 850 and 900 kilopascals to find the best SG for your case. So interpolate between this volume and this volume and 0.22222, which is what I have, state 2, and this S and this S and what you want. Okay, guys, make sense? Okay, guys, make sense? So you can get S2,
Yeah.
which is somehow 6.28 kilojoule per kilogram Kelvin. Anyway, so when you get S2, that's it, S2 minus S1. Some problems you will have S as an input. Like here you have V as an input. Sometimes you have S as an input. I will show you right now. Go to the next problem. Problem is 36, 736. Problem 736. Read problem 736, please. I'll go through this as well. Read in the book problem 736 in edition 8. I uploaded for you already chapter 6, 7 to 12 or 11. So please download them today because I'm going to remove them. In the TS diagram, he's give me 1 kilogram of R1348. It's a refrigerant we use in refrigerators. It has table 11 to A13. So this is another fluid, it's not water, from tables A11 to A13. From this table to this table. Remember, it's not water. Make sure you read the problem correctly. It's a fluid. If it's gas, like water for air or O2, nitrogen or something like that, use ideal gas. But for here, it's right, refrigerant 134A fluid. So another table. He said 1 kilogram. That's a good mass. He gave me state 1. He said T1 was 225 Celsius and P1 was 600 kilopascal. 600 kilopascal. So you have P1 and T1. He said state 2, P equal 100 kilopascal. And he said entropy is the same. S1 equal S2. This guy means delta S is 0. Adiabatic and reversible. There is no heat and it's reversible. Delta S is 0. This is called isentropic. Remember iso? Here, isentropic. Iso means the same something. This isothermal, same temperature. Isobaric, same pressure. Isochoric, same volume. Isentropic, same entropy. Ideal process. For example, Carnot cycle. If we have Carnot cycle, all of these guys mean the same thing. Delta S is 0. In the adiabatic, reversible. As long as you don't have heat and it is reversible, you have delta S is 0. So what happened, guys, here? He wants T2 required. T2 and U2, A and B. Okay, state one is so clear. You have two independent intrinsic properties. Actually, this, if it's mixture, they are not. But these two, if you go to table A11, your pressure much lower than this. It means much larger. It means you are superheated. So this is state one. If it's TV diagram, you can go this way. This is constant entropy line. So you'll have something here, for example, or here, or here. So they're going along constant entropy line. But if it is TS diagram, you just move vertically because S equal constant. So which one is better? To go this way, TV diagram, or this way in TS diagram? Which one is better, guys?
T and entropy.
It's up to you. As long as there's not ask, it's up to you. Do whatever you want to do. Some of you said, no, I would like TV diagram. I don't like TS diagram. I said, this is a constant entropy line. So I'm gonna use this is one, and maybe two here, or here, or here, or here, somewhere along this line. This is constant entropy line in TVS diagram. It's up to you. This is correct. This is, I don't care. But if I ask you to plot this, you need to plot this. Ask to plot this. So read the question carefully. So it's up to you. This is good for me. I like this one as well as you. So I like this one because it's just vertical line. So this state one is here. He said, I cool it down. So most probably it's gonna go down. So the pressure dropped. Of course, this saturation pressure became lower. Became 600, 100. It means it's low. It can be here. It can be here. It can be anywhere along this line. Anywhere along this line. So this state one, most probably somewhere here is state two. Maybe here, for example. The same here. This is one, maybe here. So what you're gonna get from these guys, you can get everything. You can get U1, V1, H1, S1. In order to get state two, what should I do, guys? I need to do two things. I have this. What else I have? What else I have, guys? What else I have, guys? I need two information to use the table. What else do I have? Huh? P2?
Entropy?
Exactly, SC2. Take this S1, put it here. Here, I want T2. So I need from T2, I'm not gonna get it. So I need everything at 2. So from state 1, only get this. I only need this. Don't get this one. Don't get this one. Don't get this one. Get only this one. Give it here. Let's say whatever value, 3.7, whatever it is. Then go back in table, for example, A12. A12, it has pressure input. And see what this value is. Is it in between or greater than the gas? If it's in between, it means you are mixture. If it's less than VF, it's compressed liquid. If it's greater than VG, it's superheated. You will find it's less than SG. It means saturated mixture. So you can get T2. You can get from this X2, which is S minus SGF over SFG. At state 2. At state 2. So state 1, you can get S1. From table what, guys? A13. This is table A13 because it's superheated. This and this superheated. Go to table A13. Open with me table A13 at pressure 600 and temperature 25 Celsius. Let's do it together. Problem 36. We need go to table A13 because it's refrigerant 134A. Oops, I went too much. A13, start with A11. Start with A11, of course. A11, if you go to 25, here, somewhere between this and this, your pressure is lower than that. Your pressure is 600. This is 650. This is pressure is between this and this. It means you are superheated. Your pressure is lower. It means you have all vapor. Your pressure is lower. So you go to A13. A13, your pressure is 600, which is mean 0.6. 0.6 here. This is 600 kilopascal. This is state 1. Your temperature is 25. It's average between this and this. Okay, so average between this guy, actually not average, between this guy and this guy. This is something confusing. Look, guys, look, guys. Guys, can you see this? Can you see these values? Yeah. The first line is called saturated line. It means at this pressure, saturation temperature is here, 21.55. But I want 25. He said you have 21, which is this one. You cannot have 20 because 20 is something else. But you have 30. So it interpolate between 21, which is this line, is called saturation. The first line at 21. It's called saturation. It's called saturation. It's called this name. This line is called saturation at 21.55 at this table. This one at 30. So interpolate between these two to get 25. For example, you want S. So interpolate between this S and this S and this temperature and this temperature and 25. So you can write it here. Actually, I used to write it here in this row. Write what? This temperature. I can write it here, 21.55, then 25. Then I want 30. Then I want 25. I write S here. Make triangles. Similarity. S minus this over this minus this equal 25 minus S saturation over 30 minus S T saturation. So you can get the S at 25 Celsius. Make sense? Just interpolate between this S.
Makes sense.
And this S to get S at 25 Celsius. This one at 21.55. This one at 30 Celsius. So you want S at 25, something in between. 20 does not exist because it's here mixture. In this pressure, it's a mixture. But there it's correct. Here it was correct because T saturation is lower. T saturation larger than 20. It's impossible to have it. That's why he give you saturation value to interpolate from the very end of X equal 1 to superheated vapors. Okay, guys, make sense? Once you get S1, it's most probably it's in between something kind of 0.93 between this value. It's 0.93, about 0.93 on average by your eyes. 0.922, 0.52, it's about 0.935 or something, okay? Somehow average. So you almost have S2. So it means that you have S2 0.935, for example. Go now to state 2. You have P2 equal 100 kilopascal. Pressure means go to table A. Danili, what does this F mean? Do not send, what is this? It's false or what? So I have a good intention. So please, if you have any question, you can ask me. Okay? Or maybe liquid, or the F is subscription for liquid. Okay? So let's go back to table now. A12. Why A12? Because we have pressure 100 kilopascal. So pressure input A12 is for refrigerant 134A. So this fluid, we have 100, which is this guy, and compare this and this. Oh, actually, this and this. Where this and this, yeah. 100, yeah. So yours is 0.92, 0.935, for example. So this is 0.88 and this is 0.95. So you are in between. So S2 is in between this guy and this guy. So you, of course, you are saturated mixture. You are in between. You have X from this S, actually between this S, sorry, and this S. So you have between, yeah, it's still in between. This is SFG. Between SF and SG, yes, you're still in between. It means you are saturated mixture. You can get X. How can get X? Here, X equal S, which is 0.935. This is 0.07. This is 0.88. SFG is difference. So you can get X. Let's say, for example, it's big here. It's about like 0.8 or 0.7. 0.7. After you get the correct S1, it's exactly S2 because it's isentropic. Only one of these, it means you can get X. If you have X, you can get U2, which is UF plus X UFG. You can get T, which is the saturated temperature. That's easy. Saturated temperature exactly at the pressure, which is explicitly given in this table. So it's minus 26.37. This is saturation temperature. So refrigerant operates at negative 26. It's a negative. So this fluid, it's a liquid phase and negative 26. It's okay. Water is not. Water, of course, at 100 Pascal, it's zero, almost 100 Kelvin, 100 Celsius. It starts to evaporate at 100 Celsius. Okay, guys, any questions? Any question, guys? So next lecture, we're gonna dive in something very important. It's called T delta S relations. It's actually in the end of this lecture, but it's very good. It's called T delta S relation 7.7. It's a very important thing we're gonna talk about, and we're gonna talk special cases for solid, of course, liquid and gases. And we're gonna go also for gases, ideal gas. That's very important. So for example, if you have gas, PV equal RT, U CVT, H CPT. If you have any two independent intensity properties, you can get, for example, the rest. But if you have S, how can I get S? How if I have S, go back. So if you have V and T, from V and T, you can get P. From T, which you have, you can get U, you can get H. How about X? Ideal gas, like the superheated region, only for gases, air. So how about S? We're gonna talk about this next lecture. Okay, guys? Any problem? Any concern? Anything is not clear?
No.